From Hypersonix and their launch window to a confidence test at NASA not being overly confidence-inspiring, and the next generation of climate change monitoring. This is a wrap of the past week of Talkin' Science Daily Bites. Hypersonix Launch Systems, from just around the corner from Trekzone HQ, has announced the launch window for a landmark flight test that will move sustained hypersonic flight closer to operational reality. Launching on board the That's Not a Knife Rocket Lab flight, and that's exactly how you have to say that flight name, the Cassowary VEX mission is targeting a no earlier than date of later this month, with confirmed launch details apparently only to be released 24 hours in advance. The first flight of DART AE, a 3.5 metre scramjet-powered hypersonic aircraft, will validate advanced propulsion materials, sensors and guidance systems in real-world conditions. After years of testing in the University of Queensland labs, and they opened their new facility around the corner in Carroll Park, and Trekzone was there. Now, unlike conventional scramjets powered by kerosene, the Spartan engine uses hydrogen, producing zero CO2 emissions and offering a reusable, low-maintenance solution for a myriad of high-speed defence and aerospace missions. This flight will be the proof in the pudding for Dr. Michael Smart, co-founder of Hypersonix, developer of the technology, good friend of the channel. We've been catching up with him for quite a number of years through all of this process. Looking forward to that first flight, and good luck to the entire team. NASA engineers are reviewing data from a February 12 confidence test of the Space Launch System that's at the heart of the Artemis 2 mission. Operators partially filled the SLS core stage liquid hydrogen tank to assess newly replaced seals in an area used to fill the rocket with propellant. However, issues with the ground support equipment reduced the flow of the fuel source once again, and while some confidence was gained in several key objectives being met, the issues are presenting themselves at the same time as during the wet dress rehearsal and also during Artemis 1. They thought they had a fix, but engineers will need to go back to the drawing board ahead of the second wet dress rehearsal later this month, with that seemingly in doubt until they can fix that fuel leak. A Sydney PhD student has recreated a tiny piece of the universe inside a bottle in her lab, producing cosmic dust from scratch. The results shed new light on how the chemical building blocks of life may have formed long before Earth existed. Linda Loserdo, candidate in materials and plasma physics in the School of Physics, has used a simple mix of gases, nitrogen, carbon dioxide and acetylene, to mimic the harsh and dynamic environments around stars and supernova remnants. By subjecting these gases to intense electrical energy, she generated carbon-rich cosmic dust, similar to the material found drifting between stars and embedded in comets, asteroids and meteorites. Her results are published in the Astrophysical Journal of the American Astronomical Society. That composition features carbon, hydrogen, oxygen and nitrogen, collectively known as CHON molecules, which are central to many organic substances essential for life. We no longer have to wait for an asteroid or comet to come to Earth to understand their histories, Ms. Loserdo said. You can build analog environments in the laboratory and reverse engineer their structure using the infrared fingerprints. Cosmic dust is known to form in extreme astrophysical environments where molecules are constantly bombarded by ions and electrons. Scientists can identify this dust in space because it emits a distinctive infrared signal, a molecular fingerprint if you will, that reveals its chemical structure. The dust produced in Ms. Loserdo's experiments showed the same telltale infrared signatures, confirming the laboratory process closely mirrors what happens in space. Marking a significant step towards a quantum-secure internet, researchers have demonstrated device-independent quantum key distribution, or QKD, over optical fibers spanning 100 kilometers. The findings show that cryptographic security can be guaranteed with this method at the metropolitan scale, which represents a much greater distance than previous efforts, and help to close the gap between proof-of-principle quantum network experiments and real-world applications. Early forms of QKD derive security using trusted devices, yet suffer from technical limitations and vulnerabilities. A more advanced approach, device-independent QKD, or DIQKD, derives its security directly from fundamental quantum phenomena, specifically the violation of Bell inequalities, without requiring trust in quantum devices' internal workings. However, the device-independent method is extremely demanding and requires the creation of high-quality entanglement and efficient detection over long distances. To date, DIQKD has only been demonstrated over short distances and in laboratory-based proof-of-principle experiments. But now, Bo-Wei Liu and colleagues report the realization of DIQKD between two entangled atoms linked by 100-kilometer optical fibers. By combining advanced techniques such as single photon interference, quantum frequency conversion to low-loss telecom wavelengths, and noise-suppressed photon emission, the research team successfully distributed high-fidelity entanglement over long distances, achieving provably secure quantum key generation over 11 kilometers with finite data, and showed that positive key rates are possible even at 100 kilometers. According to the authors, the achievement extends device-independent quantum key distribution distances by more than 2 orders of magnitude compared to previous demonstrations. A sea ice scientist at the University of Tasmania is part of a new NASA satellite mission designed to deliver greater global coverage of land, sea and ice than all prior missions combined. Dr. Alex Fraser of the Australian Antarctic Program Partnership at UTAS is a collaborator in the program led by the Scripps Institution of Oceanography at the University of California in San Diego. NASA announced at the beginning of the month that the Earth Dynamics Geodetic Explorer EDGE satellite program has been selected for continued development and is planned for launch no earlier than 2030. When it'll use new laser technology to scan the height of surface features in 120-metre wide strips around the globe, providing better coverage and higher resolution than any previous satellite altimeter. Dr. Fraser said the EDGE satellite will be the first spaceborne laser altimeter system to monitor the impacts of climate change on terrestrial ecosystems and ice simultaneously. My work involves tracking how sea ice coverage around Antarctica is changing over time under global heating, and this satellite will revolutionise that research, she said. Daily Bites on our socials first, plus a deep dive into the headline of the week on our YouTube channel. Like, follow and subscribe for more. Help this one-man band get more than 6 members. Go on then, give us a shot. Help us do more. Get the details and sign up for at the Trekzone/support.